Hello. Hi, I'm Grigore Rosu. I am an educator and an entrepreneur, so I wear two hats. This is my academic hat. And my company, Runtime Verification, is known for being a security auditor in the blockchain space. I hope the best. The best using formal methods and formal verification, for sure. But I would say that if you think of us as the best formal verification security auditor, you're not thinking big enough. So I hope by the end of this talk, I'll convince you that what we develop is a lot more than just an infrastructure and a framework for security auditing. We develop a technology that can transform the way we think about computing and we think about programs. Before I get into details, let me tell you at a high level what's going on in our field of programming languages and programs. So to tell computers what to do, we use programs. Programs written in programming languages. Programs which, in order to be executed, they need tools. Tools like interpreters, compilers, or in order to reason about these programs, we need model checkers. We need formal verification tools. We need tools. And these tools help us execute programs. For example, factorial of 3 equals 6. In order to get that, you need a tool that will take the program and execute it and give you 6. In order to be absolutely sure that a smart contract does what it is supposed to do, that it is correct, you need tools that allow you to prove that. And that's what happens in our field, in the programming language field. And this comes with two major pain points. Sometimes these pain points are so subtle that we don't even see them. Okay, so one pain point is in the world of developers. So the developers waste a lot of time redoing work. Okay? So when you implement an interpreter or a compiler for a programming language, you do almost the same work that you do to implement an interpreter or a compiler for another language. So there are lots of PhDs wasted redoing the same thing over and over again just for a slightly different syntax, a different programming language. So it's not only wasted talent, but this is also error-prone, and it's out of sync. It's hard to keep track with all the versions, and so on and so forth. So that's on the developer side. But also on the user side, on our side, consumer side, there is a lot that we have to trust. For example, why should you trust that factorial of 3 equals 6 if a program tells you that? Why? Or why should you trust that a program does a certain thing, that a smart contract is correct with respect to some property? Why? Because runtime verification audited it? Yes, that can give you some confidence, hopefully high confidence, but it's still not the absolute certificate of correctness that you'd like to have. So there is a lot to trust. So pain points for developers, a lot of duplication of work, and pain point on our side, users, that we have to accept a lot of things, a lot of claims made by all these tools around. And this is where our vision started from. So back in 2000, 2001, I was a research scientist at NASA, and I was confronted with all these problems, like all of us here, lots of languages, lots of tools, and it was not clear what to trust, what not, and there was a lot of duplication and boring work that we had to do as developers. So we started putting down the first ideas underlying the K framework, where this is how we address the two pain points. So on the one hand, on the language side, we implemented in the K framework all these tools, interpreters, compilers, model checkers, program verifiers, symbolic execution engines, all the tools that you may need for a language, we implemented them in a generic, language-agnostic way. And on the other hand, we have a language, a meta language, that allows you to we say define or specify the semantics of your programming language. So you implement your programming language once and for all as a parameter to the framework, and then you plug and play it in the framework, and then you have all the tools for your language. That was the vision. And this separation of concerns has major advantages, some of them unexpected. In particular, this intrinsic network effect. When you fix a problem, let's say in a model checker, you fix that problem in the model checkers of all the languages. Or when you fix a problem in a programming language, or you upgrade a language to the next version, now you have all the tools for that language, upgraded as well for that language. This is a lot of power. On the other hand, on the user side, so this is for developers. Okay, so instead of having n times m combinations of language tool combinations, now you have n plus m. If you have n languages and m tools, you have n plus m things that you have to develop, and all of them completely independent of each other. So that's for developers. Now for users, what K provides, and this is very important, and very few people really, really grasp it. So I'm going to just say it straight, and then I'll repeat it at the end. Everything K does, everything any of these tools do, is searching, a best effort search, for a mathematical proof of some theorem. Okay? So everything is reduced to the basic foundations of mathematics. So the fact that factorial of 3 evaluates to 6 in Java, if I have the factorial program in Java and factorial of 3x evaluates to 6 in Java, that's a mathematical theorem that can be proved, okay, according to the mathematical definition of the programming language Java. Okay? And what K does is to search for such proofs. And it truly finds those proofs. So we instrumented all these blue boxes, all these tools, to generate evidence, basically proof objects, we call them mathematical proof objects, that indeed what they do is correct. So this gives us, as users, the ultimate guarantee that the tool does what it's supposed to do, that factorial of 3 is 6 indeed, because it's a mathematical proof that I can check independently of K. As you can imagine, K is a large system, and some people ask, how large? So I collected some data here. This is the architecture of the system that we use internally. It's huge. It has more than 500,000 lines of code right now in 4 different languages, because many of these tools have been implemented by different teams, believing in different languages. But it's all open source. And as I said, and this is very important, K has the capability to generate proof objects that you can check independently. So you don't have to trust K. You don't have to trust these 500,000 lines of code. Let me highlight one of the tools that is really very useful at the core of many other tools. So look at this program. Just happens to be in Solidity, because that's how I had the slide done. But I hope we can move all this to Elrond soon. Yes. So this program doesn't do much. It just calculates the sum of numbers up to n. And there is a tool in K called the K summarizer, which takes such a program, and the semantics of the programming language, here is EVM, the Ethereum virtual machine in K, and it executes it symbolically. It basically analyzes the program exhaustively, internally, executes it symbolically on all possible paths, and in the end, it generates such a graph, which looks very much like a control flow graph in a compiler, but it's all derived completely automatically based on the mathematical definition of the programming language. Okay? So the tool knows nothing about Ethereum or Ethereum virtual machine or anything like that. It's all driven by the semantics of the programming language. And this, actually, all these blue boxes, they are actually theorems, and all these edges are actually proofs that, yes, from here you can transit to the next thing. And this tool, this K summarizer tool, is very useful in everything we do, almost. This is at the core of the compiler, the interpreter, of the program verifier, of the model checker. So everything we do is by generating, well, lots of the things we do, first we generate such a summary of the program, and then we do our specific analysis to specific tools. All right, and this brings me to what we do as a company, where our revenue comes, because what I showed you so far is very academic in nature, very nice, very publishable, but doesn't bring money necessarily. So what we do in our company, we use this technology to help companies improve the quality of their code. Right? This is called, for some reason, security auditing, but we really think more of it like reviewing of code with rigor in mind. So we developed our own internal process, runtime verification, how we analyze projects. And it has several stages, starting with design. We like to work with our clients from the very beginning. So if you work with us, runtime verification, keep in mind that we like to work with you from day zero, basically, and to review the design, to disagree, agree, disagree again, and so on the design until we converge, and only then to look at the code. There is so much you can do before you even look at the code. Okay? Then we look at the code, then we use our tools on the code. And there are lots of different tools that you can use on your code. And finally, and there is more and more interest now in the blockchain space, as we've seen also here in several talks, many of our clients want to do post-deployment health monitoring of their contracts. And this is also very easy to do for us, or relatively easy to do for us, because we already have all the specifications, all the properties, all the invariants that the protocol must satisfy at execution time. So we generate monitors from those, and then we can monitor the health of the contract. Because even if you prove things correct, they can still go wrong. Okay? Then don't start me on that. All right. And because of the nature of the language parametricity of the framework, actually, we define the semantics of many different languages, as you see here on the right. These are complete language semantics. I mean, we can take benchmarks, test suites that people develop for these languages to test their implementations, and we test our language semantics using these test suites, and we work with several blockchains. And I would like to say that our interaction with Elrond was by far one of the nicest interactions with the blockchain team. We helped Elrond review several important contracts that I guess many of you use here, like MyExchange version 1. We formally verified multi-sig, some parts of the Ad Astra bridge, the ESDT module, and then also now we are working together on MyExchange 2. And we learned the lesson. We started talking about it even before starting to talk about code, so very early. And now also work with other major players in the blockchain, in the Elrond space, like Hatom. And we just started also an audit with HashSwap. But one thing that really excites me in our collaboration with Elrond is that somehow we together reached consensus on what could be a new auditing paradigm. When we asked Elrond, Benjamin, and Lucian how they envision our collaboration long term, they made it pretty clear, pretty early, that they don't care about nice-looking PDF auditing reports. They just want to do whatever is possible to increase the quality of the code. Okay? And we were faced with something slightly different because many of our clients really want these nice-looking PDF reports to show them to their clients to get like an approval stamp from an auditor. And we don't like that, but that's how the world is. But Elrond said explicitly, we don't care about that. We want the best possible quality of the code. Okay, great. How can we do that together? And we realized that we can do that best if we work together from the beginning. So, no gloves and no, nothing hidden, everything on the table. Let's discuss, let's argue, let's use together the prototypes. Let's try together to do things the best possible way. Or in other words, we as auditors were looking always over the shoulders, let's say, of the Elrond developers. And whenever we thought that something was not easy to analyze or to audit, we gave them feedback. They took our feedback into account. And before we knew it, both the code and the audit report were done at the same time. And everything was like a combination made in heaven. It was really, really nice. And I strongly encourage this as an approach. All right, and now to conclude, I'd like to tell you where we want to go next with the K framework. So let me repeat this is a very important fact that everything K does in the end is a mathematical proof. And a mathematical proof in logic means that you have, okay, it's down. You have a mathematical theory, here the language theory, let's say, I don't know, Rust, and then you have a task, like factorial of 3 is 6, or this contract is a correct multi-sig implementation. Okay? So you have, everything in the end becomes a proof, including computation. Execution of programs is also a proof. And we wanted to see how difficult it is really to check the correctness of a proof. So suppose that you give me a proof, a sequence of steps, how difficult it is to check it. And it turned out that you can have a very small program, the proof checker, that we call it the proof checker, that can check any proof of any claim in any programming language, or even more general, any proof of any theorem in any mathematical theory. Only 250 lines of code. So I would like to make a big claim now that this program could be the most important program that we've ever written. Because with this program, you can check everything that happens on any of our computers, phones, blockchain, everything, everywhere. So here's an idea that we started working on. Let's snark this proof checker. Okay? Only 250 lines of code. Let's snark it. And now we can take everything that we can do with K, including program execution, and generate a zero-knowledge certificate, a cryptographic certificate of correctness. And now I don't have to trust your computation. I don't even care about your computation, how to do your computation. I generate a proof from your computation, and I check that proof. Now I have an absolute correctness assurance, the ultimate correctness assurance. And we hope to get there. Once you have that, you don't need things like ZK, EVM, or Cairo languages, because you only need the semantics for them in K, and then you can do it with K for them. So yeah, I hope we'll achieve that, and why not on the Aaron blockchain? Maybe we'll have XK someday, who knows? We'll see. Thank you.